Very well. Excellent. We have an open question from last class. Does this thing actually work or not? So I asked all of you to think about it and construct examples. So let's start with a quick vote again. How many of you think it doesn't work? How many of you think it does work? Wow. All right, okay, so it doesn't workers. Anyone got a example for me you can trace through? Or is it more like a gut feeling kind of thing? Seems like it shouldn't work. That's yes.
It's more like a gut feeling, but
yeah.
For the specific case, because like it doesn't.
So let me ask you this: why does your gut have a feeling about this?
So just like thinking about the case when it goes through step by step through every neighbor, it doesn't like add the previous neighbor's visited thing to the current.
Yeah. And so what is it that you've seen that might help you formulate a gut feeling about this? Something about DAGs, is that what's causing this? Is that what's making you uneasy? Okay, so yeah.
Like with DAGs, we changed because there originally was one like return type, and then we had to change it.
Yeah, we had to change the return type. We had to do this threaded computation, right? So that's what you're thinking, right? So, okay. I assume many of you were in class when we did DAGs. At least some of you look pretty familiar to me, right? So, I mean, none of you, half of you don't look like anything like the photographs you submitted brown, but that's a separate matter. You all look vaguely familiar. I'm sure I could even point to individuals over here when we did DAGs. So, why doesn't that worry you? There's a whole bunch of you voting that this works. Shouldn't you be all like your gut, like you have different gut bacteria? Is that the point? Or like what's up with that? Like, why aren't you concerned? Why aren't you concerned?
I think there are two main cases. If we traverse an edge, it either ends in a sink type of thing, or it ends in a cycle, and I think the function terminates correctly in both of those cases.
Okay. Other answers? Well, a whole bunch of hands were up. Oh, sorry, yeah, go ahead, yeah.
In the DAGs cases, we were concerned, or our major problem was reiterating over elements we've already counted, but in this case that doesn't matter because we're not actually counting elements, we're just trying to find if there exists a path. So while it's less efficient, there's no wrong functionality that comes from reiterating over the same part more than once.
Okay. So, all right, more answers. I'm going to keep taking answers as they come. Any other answers? All the hands went down. Where are all the hands? Did you knock out everybody's hands? Is that what everyone else wanted to say? That's it? Okay. All right. Okay. So, well, that seems pretty persuasive, actually. Should we take another vote? How many of you still think that this is problematic? And the rest of you are all convinced at this point? Here's the thing. In general, this traversal strategy has the same problem that we have with DAGs, right? It has this difficulty that we're sort of visiting nodes multiple times, and in fact, we may visit, can somebody construct a graph for which this is really bad in terms of the number of times we visit a node? What kind of graph would you construct? What's your, draw for me in the sky your mental image of the graph that's really bad? There's too many hands. Yeah, something that's kind of like a large fan out, all of which come back and visit the same node, right? Imagine you have a very large fan out, all come back the same node. You're going to visit this node over and over and over again. And if it has a child, right, if it has a tree beneath it, you're going to visit the tree from every single possible place, right? So, if you had a large fan out and all of these pointed back to here, well, you're going to have to visit that node anyway to see that it's in the visited set. Right? But if you now had a bunch of stuff down here, you're going to visit it from here, then you're going to come back and visit it from here, you're going to come back and visit it from here, etc., right? So this is really bad. In general, you don't want to be doing this. But from the specific sub-problem of cycle detection, revisiting a node you visited before is not inherently a problem. Okay? We're not trying to count. We're not trying to get a precise measure of the graph. We're simply asking a very coarse question, a very relaxed question, which is, do we have a cycle? Right? And so both the answers here basically come together to tell us why it's not really an issue, because the definition of a cycle is that you get back to where you started through forward traversals. Right? That's literally the definition. That's what it means to be a cycle. Right? So there's two parts to this, right? One is, are we going to visit all the nodes that are connected? And the answer is, yeah, it's pretty evident we're going to eventually visit all the nodes because we're going to look at everybody's neighbor and all of their neighbors and so on. Are we going to go into a loop? Well, to go into a loop, it would have to be the case that you have some node which has a child, which has some node, which has a child, which has some node, which has a child, which has some node, which has a child, which is something that you started with earlier. It may not be the root node, right? You may have listed something to get to here, right? But it has to be the case to get into a cycle, you have to go back to a node that is on the current path. Otherwise, it's not a cycle, right? You went to some other random node, well, that's okay. That's just one of the nodes in the middle. To be a cycle, it has to be a node that is on the path you visited. Otherwise, you can't go into a loop, right? You see that? And therefore, simply keeping track of all the nodes you visited so far will help you avoid the worst case, which is going into a loop. Okay? What it doesn't help you with is making sure that you don't visit things over and over, and that's what this kind of pattern shows you that, right? You're going to come down here, come here, and say, oh, I have to visit all of its children, so I have to visit all of these. Done, you're going to go back, you're going to forget about the fact that you visited this node, and go back and come down and say, oh, I have this node, I have to visit all of its children. Okay? Done, go back, oh, I have this node, I have to visit all of its children. And you can see that now. Yes?
In that graph, are there intermediate nodes that are not pictured?
Yes, the spaces. Sorry. But you could even imagine, you don't even need that, right? We could.
I was thinking it's fixable if you don't have that. Because then you just take the distinct of the neighbors.
Yeah, so, but there's no distinct going on over here. The whole point is we're not doing anything like that, right? But it's trivial for me to make that a non-solution, as you pointed out, which is I could do this and now we're back to the same place, right? You can't get away from keeping track of a history of what you've seen. In the general case, right? In fact, remember, every DAG is a graph, right? It's a graph, exactly. So it's a directed acyclic graph, which is a special case of graphs. So in general, you're not going to get away from keeping track of the history. It's just from the point of view of does this go to an infinite loop, it's not a problem. Okay? We're good? So your gut feelings are pretty much right. You should be concerned. You should be worried about that pattern. It's just that for the very coarse question we're asking, it's okay. But what I'm about to do next, it's not okay because we want to do better than that. Okay? All right. Questions before I move on? Okay. So now let's do something. I want to look at this piece of code again. Okay? Actually, you know what? This is not a bad graph to have up. Just assume all the arrows are going downward, okay? Saves me from writing arrowheads. So all the arrows point down. So 1, 2, 3, 4, 5, 6, 7, 8. Right? Now, I want you to talk to your neighbors and come back and tell me what is the order in which. So assume now that we have a mechanism for remembering, right? So we're going to do the threaded computation. So we're going to remember nodes we've seen before. We won't unnecessarily see nodes again, okay? What is the order in which we are going to visit the nodes? Here's the code. And the only difference is we're going to return a visited list, and so the next time we have a bigger visited list to look through, okay? What is the order in which we're going to visit nodes? Talk to your neighbors. Yeah.
We simply don't find it before we like.
Yeah, I assume you're going to traverse the whole thing, right? We're looking for a node that's not there.
Okay, so then you go 5, 6, 7, 8, then 3, 9, 4, 5.
So when you go to 3, do you hit 5?
No, you just several.
The first node has to be 2, 3. No, it still does. The next node has to be 2. It still does. The next one has to be 5. It just doesn't go to the subject. So like 1, 2, 5, 6, 7, 8, 3, 5. But like after 2, 3, 4, because it's still 5. It just doesn't.
That makes sense.
Five, 4, 3, 2, 1. We're back. Is there the order? 5, 4, 3, 2, 1. No. Okay. So anyone want to yell out an order? Just yell it out.
1, 2, 5, 6, 7, 8, 1, 3, 5, 1, 4, 5.
Okay. So I think I heard a 1, 2, 5, 3, 4, 6, 7, 8. Is that right? Anyone say that? No. Anyone say 1, 2, 5, 6, 7, 8, 3, 4?
No.
Okay. What are the other answers?
1, 2, 5, 6, 7, 8, 3, 5, 4, 5.
Oh, okay. All right. So hold on. We got 1, 2, 5, 6, 7, 8, 3, 4. 1, 2, 5, 6, 7, 8. What?
3, 5,
3, 5, 4, 5. Any other answers? Yeah. Go.
1, 2, 5, 6, 7, 8, 3, 5, 6, 7,
Hold on. Slowly. 1, 2, 5,
6, 7, 8,
6, 7, 8.
3, 5, 6, 7, 8,
3, 5, 6, 7, 8.
4, 5, 6, 7, 8.
4, 5, 6, 7, 8. Any others? There's another hand up there. Same one? Okay. All right. So we have 3 candidates. Let's vote. How many vote for this candidate? Okay. Let's differentiate these two. Why are people voting against the third one?
Because you said we fixed it.
Because?
You said we're not going to do unnecessary.
Because I said we fixed the code and said we're not going to revisit nodes we visited before. Okay? So if I did not fix the code, then of course this is what would happen, right? That was the point of this picture. But because I'm assuming that this doesn't happen, right? Okay, how do we choose between these two now? What's the difference between these two? Yeah.
They're implementation specific, so if you filter your neighbors list for things you've already seen, then the first one happens. If you don't, then the second.
Yeah, so the question is where exactly is the checking happening? Okay? Is the checking happening, you visit the node and then you say, I've already visited this node. Another possibility is you could actually filter the neighbor list and say, I'm not even going to look at the nodes that are already in the visited list. Okay? Basically the filter is in visited is false, right? Not have been visited, and then you wouldn't even go to those nodes again. Okay? Small implementation detail. I'm fine with either of these, thinking of either of these as the answer. Okay? Basically, we're going to go down, we're going to visit all the children, come back up, go here, and notice we've seen 5 before. The critical thing is we don't revisit, we come here, we see that we visited this subtree before. Okay? Good? There's actually a weird sense in which all of you should have stopped and said, I'm sorry, we can't answer that question. Why should you have stopped and now their hands come up. Oh, okay. Why should you have stopped and said we can't answer that question? Yes.
I mean, you didn't give us like an order in which we should go from like 1 to 2 first or 1 to 3.
So the 2, 3, 4 thing, right? That was some sort of left to right ordering thing there. But you could assume. Fair point. Totally fair point. Okay. That's a totally legitimate complaint. But I'm going to solve that by saying I drew it on the board in the order in which it was stored in the list. How's that? Okay. Good. Okay. Yeah.
You didn't tell us what we were looking for Ah, I fixed that while you weren't looking. I said from 1 to 9, and 9 is sitting out over there. Ooh, sneaky. He'll do that, won't he? Yeah, okay. So, good try, but I didn't tell you that initially. True enough. Okay? What does visited actually mean? Because there's sort of two notions of visited here. There's this point at which you start processing a node, right? If you want to think of the computation as this machine that's running through your graph, okay? It visits 2, visits 5, visits 6, visits 7, visits 8. It's some sense in which it sort of comes back up, right? It also visits 5 on the outbound end, visits 2 on the outbound end, comes back, and then visits 3, right? There's kind of an entry visit and an exit visit, if you will, right? So there's a point, and this actually corresponds to our visited list. There's the point at which a node enters the visited list, and then there's a separate point at which we finish processing a node in the visited list, right? It's in this intermediate state where if we come back through a sort of cross edge, we say, you've started visiting this, therefore I'm not going to reprocess this. But that's not the same as saying I've finished processing it, right? There's an entry point, an exit point. When you look at the traditional literature, so I'm just going to teach you the terminology because when you look at other books, you will see these words. They will tend to paint nodes as white, gray, and black. White nodes are nodes that have not been visited at all. Black nodes are nodes that have been completely visited. You've come in and you've finished going out, you've finished processing them. Gray nodes are in that intermediate stage where they've been added to the visited list. That means you remember, you're keeping track of the fact that I have started processing this. If I can trust the thing that's going to process this, I don't have to process it again, right? There's that element of trust, right? Why can I not visit something when it's in the visited list? Because I assume that something else is taking care of it and will do so correctly. Gray means I'm in the visited list, but the processing has not yet finished for that node. Okay? Just when you look at other literature on graph algorithms, you'll see these terms. You'll see white node, gray node, and black node. And so I'm just telling you the words so that you know when you recognize them, you'll see them later on. Okay? So you make sense, right? Every node is in 3 states. It's never been processed. It's completely processed. It's in the visited list, but the processing has not yet finished. So what does processing has not yet finished mean? So take the node 1, right? It's the first node to go into the visited list. But it's the last node such that all of its neighbors have been completely visited, right? So it's in the gray state pretty much the whole time, right? We go to 2. It goes into the gray state. We go to all of its neighbors, which is 5. We visit all of its neighbors. When we finish with it and we come back out, it's still in the visited list because just in case some weird cross edge comes back to it, we need to know that, right? But essentially it's gone to black because all of its neighbors have been visited. It has no forward edges coming out, right? Now there could be some other edge like this. Actually not even from here, right? Sorry. There could be an edge like this, right? So 2 has no way of knowing there's some edge coming into it, right? I say no, it's a node, right? It doesn't have any intelligence or anything, but yeah, I'm going to anthropomorphize a little bit. So 2 goes into sort of a black state because all of its neighbors have been processed. So when 3 comes, it's going to see 2 on the visited list, but 2 has already been finished being processed. That's the sense in which it's now a black node. Okay? And for what we're talking about right now, it doesn't really matter. It sort of matters. But later on, when you get to other graph algorithms, it really will matter whether you're looking at a gray node or a black node. You'll get to algorithms called things like strongly connected components. We won't do them this semester, but there are other graph algorithms where it really does kind of matter what the shade is on the node. Okay? So. All right. Now, what we just did, this order of traversal, is what is called depth first traversal. Okay? Now, if you've had some prior high school, prior CS, you may have heard of this as depth first search. I'm choosing to not use the word search because it's a general strategy for traversing a graph. What we do on that strategy could vary. We might be searching for something. We might be checking for reachability. We might also be trying to construct a different kind of graph, like this thing I mentioned, strongly connected components, that has nothing to do with searching. Okay? So depth first is a notion of traversal. what we do when we traverse, it's just like map or filter is a traversal. What we do when we traverse is, well, in the case of filter, we might be trying to exclude elements. In the case of fold, we might be accumulating elements. In the case of map, we might be mapping elements, right? There's a difference between the traversal and the action. And when you do higher order functions, it becomes very clear. There's a traversal strategy. You pass it the function that says what you want to do. The same way you want to think of depth first traversal as a traversal strategy that might take as a function, what do you actually want to do while you're traversing your graph in that particular order? Okay? So as you can imagine from the name, there's an alternative which is called breadth first traversal. Okay? Talk to your neighbor and come back and tell me what the traversal order is going to be on that graph for a breadth first traversal. Go.
6, 7,
How we do that without like.
Yeah, I think all the things, you can just check like this.
5, 4, 3, 2, 1. We're back. Okay? So notice when we talk about a traversal, all I need to talk about is the starting node for the traversal. Right? So implicitly we're taking 1 as our starting node. Okay? I don't need to talk about what node I'm looking for. That's a question of what we're going to do while we traverse. I might say, well, I'm trying to search for a particular node, like I'm searching for the node 9. Well, at that point, that's the thing, that's the function that's going to say, stop traversing at this point. Right? So you want to think of it like a fold. Right? It's given a particular element, and given an element and given what you've done so far, it decides whether to go on or whether to stop. Okay? So, what's our breadth first traversal going to visit here? What's the first thing?
1,
Next thing?
2,
Next?
3, 4, 5, 6, 7.
Okay, good. Okay? So breadth first traversal means you look at all of the neighbors, the immediate neighbors, before you look at the neighbor's neighbors. Okay? So in a social networking graph, it would be correspond to talk to your friends before you talk to your friends of friends. Right? So the critical thing is that the code we wrote previously intuitively maps to a depth first. We didn't even ask the question, what order do we go in? Right? It's just what we get for free. If you use a recursive process, you will automatically go to the first child, and then you'll go to the first child, and you'll go to the first child. Okay? And that's what you get for free in some sense. In a breadth first traversal, you can't go to the first child right away. You've got to keep track of all of the children, and you have to process all of the children before you go to any of the children's children. So here's what happens. I'm going to come to node 2, right? So I'm going to say, okay, what's the first thing I have to visit? I have to visit 2, 3, and 4. When I come to 2, I'm going to keep track of 5, right? So I start off and say I'm going to visit node 1. Okay, what are node 1's neighbors? 2, 3, and 4. I have to keep track of those. When I get to node 2, what are its neighbors? Well, 5. But I need to make sure I don't visit 5 before I finish visiting 2, 3, and 4. Right? So I need a data structure that's going to let me add sort of 5 onto the end. Okay? And now when I get to 3, what am I trying to add onto the end? When I get to 4, what am I adding onto the end? Okay? So now meanwhile I'm done with this, I'm done with this, I'm done with this, I'm done with this. I get to 5, what am I adding on to the end? 6, 7, and 8. Okay? And now I'm done with this. Right? Well, in my visited, so the question again, we can either filter out whether to even add it or not. Though at the point when we're adding it, we can't really filter it out because we haven't visited 5 yet. Right? We still need to keep track of the things that I visited to know that 5 has been visited. And now I get to 6, 7, and 8, and I have no subsequent children. Okay? Make sense so far? Yes?
So why did you add 3 copies of 5 and only 1 copy of 6, 7, 8?
Why did I add, good question. Very good question. Why did I only 1 copy? So, when I get to 2, I record all of its neighbors. So, I put down 5. When I get to 3, I record all of its neighbors. When I get to 4, I record all of its neighbors. When I get to 5, I record all of its neighbors. But when I get to this 5, I know I've already finished processing 5. So I first check for the visited list before looking at the neighbors. Since 5 is in the visited list, I don't even look at its neighbors because the first thing I do is check, have I already visited this node? That's why. Yes?
Wouldn't it be better than to keep like a data structure like a set where you don't allow duplicates or something like that?
You could imagine doing that, but the ordering is really important. The ordering is really, really important here for a reason I'm about to tell you about, right? And so because the ordering matters, I really want to keep putting new things at the end. And at the end implies order, and that means a set's not quite the right thing, right? So you could imagine that I have a thing that says, before you add it to the end, check whether it's already in there, right? But just remember, this example is actually illustrative, right? At the time when I add this 5, this thing is at the end, but I haven't yet visited it. So it's a little subtle to get the exact ordering right, okay? Yes?
So why would you use a data structure over just like looping over the neighbors to check if they're the one you're looking for, and then looping over them again to look at their children? Like, doesn't that accomplish the same thing without having another data structure?
So, I don't fully understand your proposal, but let me try to answer it at a higher level, okay? There is always a data structure. So even when we did depth first search, there was a data structure. The data structure was the sequence of function calls that we had made. Do you remember we looked at Tracer? The tool that showed us the sequence of function calls, and it showed us the set of calls that had been made, the calls that were pending, and if you did the click the next button, it shows you call being made, call returns, next call is made, returns, goes up, next call. So there is a data structure, it's inside the computer, it's called a stack, it's called the running stack of the program, and that data structure exists anyway. We just got it for free. So we didn't think of it as an explicit allocation and we have to allocate and deallocate, okay? We could have done it explicitly. We could have said we're going to have an auxiliary data structure, put the nodes very explicitly on that data structure and taken them off, and that would have made very explicit what we're doing. We just got it for free, and it's actually more efficient if we let the computer deal with it, so we didn't really ask any questions. But there is always a data structure, right? And what you're trying to do, I'm not actually convinced would work. I'd have to think harder. Or you're actually going to have to convince me harder that it's going to work in general. So let's put it that way. It's not my problem. Yeah. Okay? So I'm not sure it's going to work because you're trying to simulate a non-stack with a stack, and that's at least non-trivial or might involve a lot of extra traversals. I'm not quite sure depending on the concrete proposal. Okay? Yeah.
What are the benefits and disadvantages of depth first and breadth first?
About to get to that. Great. Thank you. Good. Perfectly timed question. Okay? So this data structure where we're always adding things to the end, right, is called a queue. Okay? In particular, the first thing in is the first thing out. Okay? The last thing in is the last thing out. In contrast, what we did over there, this data structure, as I said, is a stack, and it has the property that the first thing in is the last thing out, or the last thing in is the first thing out. Right? Because the first thing in is the last thing to eventually get finished on the traversal. The last thing to get visited is the first thing to finish traversing. Okay? So, these are two standard data structures you're going to see in computer science, stacks and queues. So what you have to do when you're doing this as a breadth first search is you have to maintain an auxiliary data structure because you can't rely on the running stack to do your work for you. You have to maintain an auxiliary data structure, and essentially you have to keep adding things to the end of the queue. How do you implement a queue? Well, that's what lab's going to be about. So in lab you'll actually see, in fact in lab you'll see a really cool way of implementing a queue. And I mean, it's not hard to implement a queue, right? What do I want? I want to be able to add an element to the end of the queue, and I want to be able to take an element off the front of the queue. How would we do this? Let's say we have a list. How do I take the first element off the queue? First. How do I add an element to the queue? Append. Done. Okay? This is completely trivial. You can all do this in your sleep. Okay? Well, what you'll see in lab is a clever way of doing it. It's like one of the most beautiful, beautiful little clever, cute things in computer science. So it's good for you to see it. Okay? So go to lab and see a cleverer way. All right? Okay. And it's going to turn out it's a way more efficient way, in a way you can't even prove. You're going to do the big O analysis of it, and it's going to be just as bad as the list. And we're going to have to teach you a new way of doing program analysis just to show that it's efficient. Okay? All right. All that's coming up. So, what is the virtue of the depth-first search? Well, there's kind of two ways to think about it. One is three ways. One is it's the thing we get naturally. It's reasonably efficient. There's actually a weird advantage it has. It actually visits nodes in kind of a parenthesized order, right? It sort of wraps nodes in parentheses. Essentially puts a giant, because this is the first in and the last out, right? Second in, third in, fourth in, right? Fifth in, sixth in, seventh in, close, 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 right? So it basically gives you this nice parenthetical structure that every sub-node is visited starting later and finishing earlier than the parent node. That's the parenthetical structure that it gives you. Okay? That's cute. It has some applications, but this is far more interesting because what breadth-first search gives you, starting from a root node, okay, you visit a node before you visit any of its children. That's by definition of what it means to be breadth-first search. You visit all the children before you visit all the children's children, before you visit all the children's children's children, right? So what that means is the length of the path from the root to the point you got to in the breadth-first traversal is the shortest distance from the root to that node. So breadth-first search actually lets you for free essentially compute the shortest distance from a starting point, wherever you started the traversal, to every other node in the graph. Okay? It gives you the shortest distance. And that's a really nice property. Because if there were a shorter path, so essentially if there were, let's say from here to here, right? What's the distance from here to here in the graph? Shortest distance. 2. If there were a shorter distance, the only way there could be a shorter distance is if there was a path from 1 directly to 5. But if there had been a path directly from 1 to 5, what must have been the case? 5 is actually at the same level as 2, 3, and 4. It's a direct neighbor of 1. Therefore, we should have visited 5 before we got to 5 from 2, 3, and 4. We should have gotten to 5 directly from 1. Right? And therefore, that contradicts the claim that we've actually done things in true breadth-first order. Okay? You can generalize this into an actual proof that says that we should have visited a node in the shortest number of steps that there is, starting from the root. Well, that's now a really interesting property. It's really interesting because now we can start to use graphs to plan things. Right? People actually use graphs for real in planning all sorts of things. For example, every time you pull out Google Maps and you ask for it to give you a path from one place to the other, it's trying to give you the shortest path. Well, how does it compute the shortest path? Well, it's not surprising that it has a graph that represents all the nodes, and the vertices are points and the nodes are the roads, right? But it needs an algorithm for figuring out a procedure, a method, okay, to figuring out how, of all of the possible paths there are, how to find your path and actually prove to you that it's the shortest one. Well, we just saw our first hint of that. Okay? Basically, it's a form of breadth-first search. Except, is there something unrealistic about our graph model when it comes to, say, Google Maps? Something missing?
In Google Maps, the edges have points, right?
Yeah, I mean, it doesn't just say you're 5 hops away, right? Some of the hops are very different from some of the other hops. hops, I'm sorry, networking term, hop is like a jump, right? One node that you, one edge that you traverse is called a hop, okay? Because people think of packets hopping from routers to routers, so that's where the term comes from, okay? So in a real map like Google Maps, you're actually going to assign weights to these things. Now, in a social network, you're not actually allowed to, right? You're not allowed to say, well, you know, she's like a 0.8% friend, you're like a 0.6% friend. You're not allowed to do that, right? I mean, Google, I mean, Facebook knows that about you, they just don't tell you, right? So you're not allowed to assign weights on some graphs, right? It's literally the case. On social network, you're not allowed to like rank your friends and things like that, right? You just have friends and they're all like considered one homogeneous group. But when you get to a graph like a road graph, there are real differences. There could also be toll might be a difference, right? How much toll do you pay? Or at this hour, how much is the estimated travel time, which may be unrelated to distance? Anyone from LA? Yeah, exactly. Okay, okay, right? So, it doesn't matter what the measure is. The point is that the edges have weights on them. And so the question is, how does something like Google Maps actually determine what I will call the lightest path? Okay? So this is not the phrase that you'd normally find in computer science textbooks. For some reason they called it the shortest path, which is really misleading because breadth first search gives you the shortest path. But once you start adding weights to the edges, you don't want the shortest, I mean, you might still want the shortest path, in which case you can just use breadth first search. But sometimes what you typically care about, the reason you add weights, is you want the lightest path, right? The path that has the least amount of weight on it. We've screwed up our terminology, it's too late, sorry, okay? So when people say shortest path on a weighted graph, they actually mean the lightest path. I'm going to use the term lightest because I want to be a little precise about this. Make sense? Shortest versus lightest, two different concepts? Okay, so on breadth first search, basically what we're saying is generically our graphs, everything has a weight of 1. But if everything doesn't have a weight of 1, then things get more complicated. Now, this lecture, just to preview where I'm going, this lecture is actually split in 2 parts. It's unfortunately split between Monday and Friday. I'm going to introduce the idea on Monday, and you're going to work through some examples on Friday. Okay? But you'll also work through many more examples because it's the homework that's going out today. Okay, so by tonight we'll have the homework published, and that's the homework, so you will, I guarantee, work through lots of examples. Okay? You will, right? Yes, you will. You're good people. Good. Okay, so I know I can trust you, right? You're not going to betray me, are you? You're not going to betray me, are you? No. Are you going to betray me? No, that's not. Wow, there's no conviction at all here. None at all. Okay, at least you're honest. You may not be good, but at least you're honest. Okay, so I'm going to work through the algorithm quickly. Wes, what? Yeah.
We're pirates.
Thank you. Okay, so we're gonna. Yes, this is self-inflicted, isn't it? So we're gonna work through this quickly in class. You're going to do more examples. I'm not going to work through a detailed example in class. You're going to work through examples on Friday. The reason we're split between today and Friday is because I'm out of town on Friday, so Tim's going to come to class and work through examples of both this and the thing I talk about tomorrow. Okay? So I'll show you one graph algorithm today. I'll show you a completely unrelated graph algorithm. Actually, I'll show you 3 unrelated graph algorithms. Well, they're all related, but for a different problem on Wednesday. And on Friday, I'll work through examples. Is that clear? Okay? So don't panic that you haven't seen any serious examples in class today. Okay. So the lightest weight algorithm is basically a generalization of breadth first search. Okay? So, and it's due to a pretty remarkable computer scientist called Dijkstra. So that's an IJ, but he's Dutch, and so it's not it's the J it's an I. Okay, it's an E actually, if you want to get precise about it. Okay, so here's the idea. Okay. We've got a graph. So we've got a graph. What we want to do is, given a starting point, given some starting vertex, we want to know what is the distance, the lightest distance, least distance, to all the other nodes in the graph. Okay? Now, initially, we're going to say, well, what is the distance from a node to itself? What is the lightest distance from a node to itself? We're basically going to assume axiomatically that that's 0. Okay, always additive identity in this case. Helpful to assume that the distance from a node to itself is 0. Okay, so we know that the distance from this node to itself is 0. We don't know anything about its distance to any of the other nodes. Okay. Now, we're going to look at all of this node's neighbors and ask, what is the lightest weight edge going out from this node to all of its neighbors? Okay? If you think about it, at the starting point, right, we're going to work inductively. At the starting point, that has got to be in the graph, because let's say this node, this thing here is 5, this thing here is 10. Okay? This edge that would put this at distance 5 has got to be part of the answer, because every other path to it, even if there is a path, has got to be at least, has got to be bigger than 5. Right? We're making an assumption here, which is that we're actually assuming that node weight, the edge weights are positive. Okay? Now, can you have 0 edge weights? Can you have negative edge weights? Does it make sense for a graph to have negative edge weights? Negative? Negative?
Just like an accident or something, you don't want people to.
Oh, that's interesting. So an accident is actually a disweighting of the edge, right? Or like you literally want to push people away from the edge. Any other examples of negative weight edges? Negative weight.
If we're having tolls as the weights, then
Tolls, okay, so that's another kind of thing. You maybe want to dissuade people unless people want to pay the tolls.
Where the negative weight would be a government subsidy to take that road.
Oh, very clever. Okay, so yes, okay, good, yeah.
Similar to that selling and buying of things.
Selling and buying of things, okay. So discount rates, right? I mean, interest rates sometimes go below 0. Nominal interest rates go below 0. So in trading situations, you could have negative rates, right? They're literally negative rates. So the point is, we're going to assume that the rates do not go below 0, and I'm just going to assume they're not 0 either, okay? Doesn't actually matter if we assume they're 0. Negative rates will completely, what's the problem with the lightest weight edge on a negative weight graph?
Might not be there.
What is the lightest weight? If I have weight of 1 minus 2, right? I can just go as many times as I want around in this loop, right? And I can keep getting lighter and lighter paths, right? Okay, so what you really want is, if you have a cycle with a negative weight, you want to be warned about it. You want to be told your graph is broken, okay? The algorithm I'm going to show you is not going to do that. You will see that in lab. If we're going to do that in about 3 weeks or so, right? You'll see an algorithm called Bellman-Ford that'll deal with that. So I'm going to assume that that's not an issue for now. You'll see it by the end of the semester, okay? So, the point is, to get to this, if this is an edge of weight 5, any other path has got to be at least 5, if not bigger, right? And if I assume everything's positive, it's actually strictly bigger. So, it doesn't make sense to include any other paths to get here, right? So this is the lightest weight edge. I want to take this edge, and now I know that this is a weight 5. Yeah?
Can you have 2 edges with different weights going to the same?
No, we made that assumption that we're not going to deal with those graphs. Yeah, so otherwise this algorithm wouldn't work in that case, except you can modify it, but I'm not going to get into that here. Okay? Okay, so now we're going to look at all of the neighbors of all of the edges that are already in the graph. Right? Initially our graph had 1 node, now our graph has 2 nodes. We're going to look at all of the neighbors of all of the edges that are in the graph and take the lightest weight edge. Okay? So initially, when I had this node in the graph, I had a candidate weight for this point over here, right? For this vertex. My candidate weight was, well, it looks like it could be 10, right? I could kind of record this as an initial guess. It could be 10. This could be 5. Well, 5 is my best weight, so I'm going to take the 5 and add this to the graph. The moment I add this to the graph, I need to update the other things, right? So I'm going to update this to say, actually, there's a better candidate weight, and that candidate weight is 8, because I can come here and go here instead of taking the 10 over here. Okay? But I can update all of these, and so now here I have something that is potentially a weight 7. Right? So now again I'm going to look and ask, what is my lightest weight edge? Well, my lightest weight edge is the 2, and so I'm going to add that to my graph. So this now becomes part of my graph. Right? So now I've got 3 nodes in my graph. And what are the out edges? I've got a 10, I've got a 3, and I've got a 4. So at that point, I'm going to add the lightest weight edge that's adjacent to my current graph. Yes?
What's the weight of the direct path from the initial?
Oh, I was assuming that had a higher weight. I should have written this down. Sorry. Let me write these. Okay? Sorry. I had them in my head and didn't write them down. That's bad. Sorry.
No matter.
Okay. Okay? So now my lightest weight edge becomes this. And now this is the one I'm going to take. So that now adds this to my graph and gives me a weight of 5 plus 3, 8 to get to here. And now I'm going to look at all of my adjacencies. So I had an initial guess of 14 over here. Now I've got a guess of 10, which is better. And I have an 11, which is not better than the 10. So I'm going to take this, adding this one. No, did I get that wrong? Yeah, no, that's right. Yes?
So your approach was to take the edge that was the lightest out of the set of edges that are visible right now.
Out of the, right, so I have a set of vertices that I keep growing. Every time I grow it by one vertex. And the way I grow it is I look at all of the vertices I have currently added, look at all of its neighbors, and take the lightest weight edge.
Isn't it the latest weight edge plus the current weight of getting to that node? Because if you had like 1, and then you had 2, that would take this, your algorithm would take this path rather than this one.
Good question. Which one should we do?
This one.
Okay, I was hoping to force somebody to construct a counterexample, right? So what you want is you want the lightest weight combined with the weight that you've already computed for that node. Okay? Does that make sense? Yeah. That's the counterexample I was hoping to get to, but yes, good. Thank you. Yeah. So just to be clear, here's what the counterexample looks like, right? So I have 1, 1, 1, 1, and I put a 2 over here, right? At this point, initially I want to take this one, right? Because that gives me a 1. Now I have 2 candidates because this is 1 plus 1, 2. This is also 2, so let's say I take this, right? So now this is in, and now I still have a 1 plus 1 over here, and so then all of these get added, but this one has a lighter weight edge, which is 2 rather than taking this. Okay? So the point is you want to take the sum of, you want to get to the lightest, you want to take the lightest path you've gotten so far, and then ask what is the least thing I can get to from there. Okay? And that's the generalization of the breadth first algorithm. Okay? So it's going to take us some time to develop more of an intuition for this. We're going to build this up. It's written up in the text, so please take a look at the text. And we're going to do more examples come Friday. Okay? Questions? Yeah.